So here's your instructions for how to predict molecular geometries. Draw the Lewis structure for the molecule. Determine the total number of electron groups around the central atom. Determine the number of bonding groups and the number of lone pairs around the central atom. And then I disagree with the book's fourth instruction here. They say refer to table 10.1 to determine the electron geometry and molecular geometry. Well, that's great if you have table 10.1 in front of you, but you're not going to have that on an exam. So we're not going to do that. Think about how balloons would arrange themselves and imagine that lone pairs are invisible balloons. So let's do some examples. Predict the molecular geometry and bond angle of ClNO. The way these atoms are arranged in the formula is suggestive of how they are arranged in the structure. So if you're not given any other directions, I would assume that the nitrogen is in the middle and the chlorine's on one side, the oxygen's on the other side. I will not try to trick you with things like that on an exam. I would probably say the nitrogen's in the middle. Here's nitrogen, and we put oxygen over here and chlorine over there. First thing we have to do is draw the Lewis structure, because we can't just say, oh, well, that must be linear because there's two atoms. It depends on the lone pairs. So chlorine has 7 valence electrons, nitrogen has 5, oxygen has 6. So that's what, 18? Yes? Well, I don't for sure, but the way this is arranged in the formula suggests that the nitrogen should be in the middle. It's not always like that, but like I said, I won't try to trick you. In the test bank, a lot of times it does things like this. It'll underline the central atom. Sometimes it does matter what the central atom is. Other times it doesn't matter. Yeah, so those are good questions. So 18 electrons. We've got 2 and 4 in the bonds. 6, 8, 10, 12, 14, 16, 18. Ran out of electrons. So what do we do? Double bond. Share more. So the nitrogen here has an octet and the oxygen doesn't. And so I'm going to take a lone pair from the guy that has enough and share with the one that doesn't have enough. It's kind of how sharing works, right? Yes?
We can kind of predict what, like for nitrogen and oxygen, because their charges on the periodic table are, like for nitrogen it's -3, it likes to have 3 bonds.
Yes.
And then the same for oxygen.
Yep.
That's why we wouldn't pick it to double bond before.
That's why I would pick the double bond to oxygen, because just anticipating that this is supposed to have the lowest possible formal charges. Oxygen tends to make 2 bonds, nitrogen tends to make 3 bonds, chlorine tends to make 1 bond. And so if you recognize that, and you can, like you pointed out, it's the number of bonds is equal to the negative charge that they have, which I actually hadn't thought of thinking of it that way. Nitrogen has 5 valence electrons, and if you draw the Lewis symbol for nitrogen, there are 3 lone electrons here, unpaired electrons. Each of these will very nicely form a bond with something else, and so we get the 3 bonds. And then those are also the 3 electrons that get lost. So if you recognize how many bonds these different elements would prefer to have, when they have that number, then there's 0 formal charges. So the halides, the halogens, chlorine, fluorine, they tend to just form 1 bond. Now the bigger ones, like they can expand their octets, but that's when there is a central atom. Nitrogen 3 bonds, oxygen 2 bonds, and so it went more smoothly because I did it because I knew what I was aiming for, but that's why. For For the purposes of geometry, if you put the double bond between the nitrogen and the chlorine instead, the geometry would be the same, right? So in that respect, it doesn't matter. So we've got octets for everybody. We've got 0 formal charges. So this is a good Lewis structure. How many electron groups on the central atom? 3. A double bond is 1 group. Yeah, that's why I keep emphasizing that. So double bond, single bond, a triple bond is 1 group. Okay, a lone pair is 1 group. If you have a free radical with a single unpaired electron there, that's also 1 group. I don't think we'll do any of those, but so we have 3 electron groups. So what do 3 balloons do? They form a triangle, right? And it's flat. So that's called trigonal planar. And I know these names are sometimes a little hard to remember. The good thing is I'll be testing you on this kind of stuff with multiple choice questions. And so I'm not going to try to trick you. There could be trigonal planar, trigonal bipyramid, trigonal pyramid, but I'm not going to put like flat triangle and trigonal planar, because if you recognize it's a flat triangle, I think that's pretty good. So I won't try to trick you on that. So this is the electron geometry. It's the geometry of the electron groups. And so we could draw a picture of that. And what's the bond angle in this triangle? In a trigonal planar? 120. So the ideal geometry would be 120 degrees. So that's our electron geometry. So our molecular geometry is where we say, well, that lone pair is invisible. So that's invisible. It's just this little lone pair. And so we're not going to count that because it's invisible, we can't see it. So then we're going to name what we can see. What shape is that? It's not fancy. Bent. So the molecular geometry, why did I write molecular group? That's lame. Because there was group above it, I guess. Molecular geometry, oh good grief, is going to be bent. With a lone pair here, how is that going to affect this bond angle? It's going to be smaller than 120. So I'll just put a less than sign there, because it does ask us to determine the bond angle. So the bond angle, I would not be able to tell you exactly what it is. The bond angle is less than 120 degrees. That's as close as we need to get.
And that's true for both the molecular structure and the electron structure.
Yeah, the electron geometry, we don't usually discuss the bond angles there. But it would be the same as the molecular geometry, where this lone pair is pushing those a little together. You want to think about the ideal angles first, and then you can go less than. Any other questions? Let's do I3 minus. Some of these are really weird molecules or polyatomic ions. So there's 3 iodines. We're not going to have any circular things that you're going to be drawing Lewis structures for, so don't try to put them in a circle or a triangle or anything. You're just going to have an iodine in the middle and one on each side. That's 3 things. They're all the same. It's going to be in a line. We have 3 iodine atoms, and they each have 7 valence electrons. And the -1 charge on that ion, do I add an electron or subtract? I need to add an electron. So that's going to give me 22 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2 extras. Where do they go? On the central atom. Iodine is period what? 6? 5. Period 5. Not group, period. It's period 3 or larger, so it can expand its octet, and so we can put that lone pair on the middle one. To finish this out, we should put brackets in a charge. So now we can look at geometry. The first thing we have to do is look at electron geometry and ask ourselves, well, how many electron groups around that central atom? 5. 3, no 4, no 5. There's 3 lone pairs and 2 bonds, total of 5 groups. So 5 electron groups. How do 5 balloons arrange themselves? So that octahedron there is 6 balloons. So if you took 1 balloon off, it's a trigonal bipyramid. The square pyramid is derived from the octahedron. So here we've got 5. Let's see. Pause. So we have this trigonal bipyramid. We have 2 bonding pairs and 3 lone pairs. In this trigonal bipyramid, where do the lone pairs go? They go around the equator because there's a little more space, right? Instead of 90-degree angles on everything, they have 120-degree angles and a 90-degree. So if we sort of sketch out a trigonal bipyramid, so these are the axial and then these are around the middle. So that's the electron geometry. And then to determine the molecular geometry, we're going to replace these with lone pairs. So that's a lone pair. And that's a lone pair. And this is a lone pair. We're imagining those as invisible balloons. And the molecular geometry is describing what's left, what the atoms are doing. What's this called? Linear. So the molecular geometry here is linear. Linear molecular geometry. Yes?
Okay, so in the center iodine,
Mm-hmm.
in the middle iodine, there's the 2, you have the pair on the top, pair on the bottom, and you have 2 single ones, and then you have the one in like the bottom corner. That's okay? Put that there?
Well, I'm trying to show 3 dimensions. That these 3 are in a plane like this one. So So if I take my ball and stick model and I pull the atoms off, those equatorial ones, that's what I'm trying to draw, is something like this. So the dots are these empty sticks. Does that help? Each single pair and each bond. So I have one bond here and one bond here, and then there's 3 lone pairs. So that's 5. Yeah, so let me see this. There's 1, 2, 3, 4, 5. Lewis structures are drawn flat, and so once you get top and bottom, right and left, then you have to squeeze the other ones in between, and it kind of gets a little messy sometimes. Does that help?
Yes.
Any other questions? So this illustration from your textbook is trying to help you understand how we represent 3-dimensional things on paper. So we use a straight line to indicate that bond is in the plane of the paper. This hatched wedge means it's going into the paper or behind the paper. And the solid wedge is coming out at you. So if we look at this one in here, this trigonal pyramid, this AX bond is in the plane of the paper. This one is coming out at you, and that one's behind. And so it's a trigonal pyramid. It's a 3-dimensional thing that's different than trigonal planar, where a trigonal planar could be drawn with all just lines, because that can lie flat in the plane of the paper. This square planar one, all of those are in the plane of the paper. The electron geometry for this one would have to have 2 lone pairs, and the lone pair would be sticking straight out and straight behind. The bent structure, there's trigonal planar. I didn't really need to draw that. The top 3 here are all planar things. They all fit in a plane, and so we don't have to use the wedges. What about larger molecules? Well, bigger molecules have more than one interior atom. So what we do is we look at the geometry around each of the interior atoms. So an example is given here. Here's our Lewis structure. This is glycine. It's an amino acid. This nitrogen, and there's 2 carbons and an oxygen that are all central atoms, meaning they have more than one bond. They're between things. So this nitrogen has 4 electron groups. So the electron geometry is tetrahedral, but the lone pair is invisible, and so that gives us a the trigonal pyramid shape over here. This carbon has 4 bonds, 4 electron groups, no lone pairs. So that's going to be tetrahedral. You see this one's kind of coming out at you, and this one's behind, and these 2 bonds are in the plane of the screen. This carbon has a double bond, which is 1 group, and 2 single bonds, which are each 1 group, so a total of 3. And so that one's trigonal planar. This one's flat. And then oxygen over here, 4 groups, tetrahedral, but 2 are lone pairs, and so this is bent. I won't make you draw something like this on a test, in large part because I don't want to have to look at your drawings and evaluate, is this good enough or not? There could very well be a question that gives you a Lewis structure and asks you about a particular atom. What is the geometry around that atom? And then based on the number of electron groups and lone pairs, you should be able to predict that. So predict the geometry around each interior atom in acetic acid and make a sketch of the molecule. So I wouldn't do this on an exam, but it could happen on a worksheet or something. So this CH3 here, or H3C, that's telling me that there are 3 hydrogens bonded to that carbon. Well, we a lot of times we don't just draw that because it gets really messy. So this is sort of a foreshadowing of what you're going to see in organic chemistry, where there's a lot of stuff like this. But for our purposes here, we need to be able to see those so that we can make the correct Lewis structure. So we're going to put those out here. So we'll start with that. Oh, and then we should also take this hydrogen and show that it's bonded to the oxygen. Just so we can see all the bonds. Are there any lone pairs in here? It matters. Well, we need to know how many electrons there are, right? We've got 4 hydrogens, each have 1 valence electron. We have 2 carbons that each have 4 valence electrons, and we have 2 oxygens that each have 6 valence electrons. So I think that's 24. In bonds, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've got octets for everybody there. So an exam question might give you this and say, okay, what's the geometry around this carbon right here? Let me erase this. So this carbon, what's the geometry around that? Well, how many electron groups are on this carbon? Electron group, lone pair, single bond, double bond, triple bond, single electron. Each of these is one group. Double bond is one group. So how many electron groups around that carbon? 3. 3 electron groups.
Oh, so we don't count the lone pairs on the oxygen?
No, you're only looking at this carbon. What's on the carbon? Those lone pairs are on the oxygen, so we're not going to look at that.
So are we just looking at our center atom?
Right now we're just looking at this carbon. We're going to look at all 3 of these interior atoms, but I just started in the middle randomly.
So we're just starting with another carbon.
Yeah, for now we're just looking at this particular carbon, and so this has a single bond, and a double bond, so 3 groups. So what's the geometry there? Triangle planar, good enough. Trigonal planar. That's the electron geometry. Are there any lone pairs? No. So the molecular geometry is the same. So let's look at this carbon. How many electron groups are on that carbon? 4. So that's 4 groups. What do 4 groups do? Tetrahedron. Tetra is a prefix that means 4. Are there any lone pairs? No. So the geometry there is tetrahedral. And then we got this oxygen. How many electron groups? 4. What do 4 groups do? Tetrahedron. So that's the electron geometry. Are there any lone pairs? There are. So that's the electron geometry. When there are no lone pairs, the electron geometry and the molecular geometry are the same. But here we have lone pairs, and so what's the molecular geometry? It looks linear, right? But 4 groups make a tetrahedron, and then you make 2 of those groups invisible, bent. That's the molecular geometry. So we need to consider the electron geometry, but when it asks what is the geometry, it means the molecular geometry. Well, this one's a little floppy, but this would be the tetrahedron, right? And then lone pairs, you make those invisible, and what's left is bent. It's not linear. But on the paper, it's drawn linear, and so I can kind of trick you that way. Okay, then make a sketch of the molecule. That's really fun. I won't make you do this, but I'll do it for you, just to sort of demonstrate. So I'm going to erase this because I need some space.
You're not going to make us draw it?
I will not make you draw it on an exam. Now the worksheet, maybe. So I'm going to start with that central atom. And so it's got a double bond to the oxygen up here. It's trigonal planar, and so these angles are roughly 120. Here's my oxygen. Here's my other carbon. This oxygen is bent structure with the hydrogen, so I can draw that in the same plane. And then when I get over to this carbon, that one's tetrahedral, and so I have to go 3-dimensional on that one. So that's a sketch of the molecule.